Now, having seen on how we can solve the determinant of a 2 by 2 matrix and the determinant of a 3 by 3 matrix, getting the adjoint of a 2 by 2 matrix and getting the cofactors of a 3 by 3 matrix, then getting the transpose of a 3 by 3 matrix. Now it's high time that we want to see their applications. Now in this video, we are going to focus on how to solve linear system of equations using cofactor method. Now, let's say you've been given equation x plus 2y minus 3z is equals to negative 9 and x plus 3y plus z is equals to negative 3 and 2x plus 5y minus 4z is equals to negative 16, and you've been told that use cofactor method to solve this linear system of equation. Now, how can you go about it? So, solution. For the first step, what we need to write this matrix in the form of AX is equals to B, where A is the matrix coefficient and then X is the matrix of the variables, then B is the matrix of the constants. So expressing that or writing the given equation in form of AX is equals to B will give us this matrix here. This is the part of A, then this is the part of the X, then this is the part of B. So these are the matrix constant, matrix of the variables, then matrix of the coefficients. Now, after writing that matrix, the equation into this form, we need to get the determinant of the matrix of the coefficients. Now, to get the determinant of the matrix of the coefficient, you can check on our previous videos on how to get a determinant of a 3 by 3 matrix. Now, here we will just go straight to the point. That one will give us negative 2. Having found the determinant of the matrix, we can now go ahead and find the cofactors of the matrix. Now, also for the cofactors, you can check on our previous video on how to find a cofactor of a 3 by 3 matrix. Here we will go straight to the point. Now, solving that cofactor will give us the final one to be negative 17, 6, negative 1, negative 7, 2, negative 1, 11, negative 4, 1. Now, after finding the cofactors of the matrix, then we need to find cofactor transposed, or the transpose of the cofactor. Now, transposing simply means changing the rows to columns and then columns to rows. So 17 will hold its position, then 6 changes its position, then negative 1 changes its position, then negative 7 changes its position, then 11 changes its position, 2 retains the position, negative 1 changes its position, then negative 4 changes its position, then finally 1 retains its position. So that is the transpose of the cofactor. Remember, transposing a matrix or a cofactor, it simply means changing rows to columns, then columns into rows. Then from there, we need to get the inverse of a matrix. And remember, inverse of a matrix is denoted as A raised to negative 1. So, inverse of matrix A will be given as 1 over determinant of the matrix times its cofactor transpose. So this is cofactor transpose. Now, the inverse of that matrix will be negative 1/2 into the cofactor transpose. Now, since that we have got the cofactors transpose of the matrix, we have got the inverse of the matrix. Now we can solve the equation. We can now rearrange our equation. We can say now the equation becomes the inverse of the matrix times the matrix itself, which is A, then times the variables matrix should be equivalent to the inverse of this matrix times the constant matrix. Now, but we know that a matrix times its inverse gives us an identity matrix. But we know that a matrix times its inverse gives us an identity matrix, meaning this part on the left side of the equation reduces to an identity matrix. Then we remain with this part on the right side of the equation. Now, solving this gives us 1, -2, 2. This implies that x is equals to 1, y is equals to -2, and then z is equals to 2. You can plug these ones back into your original equation to see whether you are correct.